Fine. Hello, everyone, and welcome to this talk. My name is Chenghao, and I'm a second-year PhD student from Nanjing University in China. Today, I'm going to present our work titled Static Belief for Gradual Typing, which has been published in the Journal of Functional Programming. So to kick things off, I'll provide a quick overview of gradual typing. So as you may know, the gradual typing is a specific feature that enables seamless integration of static and dynamic typing. This functionality is composed of two key elements, the dynamic type and the consistency relation. The dynamic type represents dynamic components in a program. And various notations exist to denote this concept. In this presentation, I will use the asterisk symbol to represent the dynamic type. On the other hand, the consistency relation is a reflexive and symmetric, but not a transitive relation. It is used to replace the equality relation, in typing rules. So to illustrate this point, let's take a look at the comparison of the application rules in gradual and non-gradual type systems. As you can see, if we move from the equality relation to the consistency relation, we will obtain the gradual version of the application rule. A crucial aspect about gradual typing is that every type is consistent with the dynamic type. So if the parameter type of E1 happens to be the dynamic type, then E1 can be applied to arguments of any type. So this essentially underpins the seamless integration that gradual typing offers. In this study, we delve into a specific issue which can be summarized as gradual typing often sacrifices too much static checking. So to illustrate this point, let's look at an awkward example under this gradual version of application rule. Consider a lambda expression which takes an integer, adds 1 to it, and returns a value. If we attempt to apply this lambda expression to a Boolean type, then the type system will promptly reject this program because Boolean is not consistent with integer. All right? However, if we slightly alter the annotation from integer to the dynamic type, then the type system will greenlight this program because the dynamic type is consistent with any type. Nevertheless, the program will still abort at runtime because it just defers the static checking to runtime. The bottom of this slide shows how this program aborts under the standard proxy semantics. So a typecast will be performed at runtime, and since Boolean can't be cast to integer, the program will abort with Boolean message B1. So in our study, we aim to strengthen static checking by flow analysis. Let's look at how this method works on this awkward example. First, we compile the program into the statically typed language by inserting two typecasts. Then we assign a unique position label to each subterm, just like standard flow analysis approaches. Subsequently, we turn our focus to flows in this program. To streamline our discussion, I've highlighted the relevant flows in this program with those arrows. So these two black arrows are just ordinary value passing relations in this program, and I've written them down on the right. Those two orange arrows, on the other hand, play a different role. They are the typecasts that have been inserted into the program. So this is one insight of our work, that typecasts can be viewed as a special form of flows that are monitored by the Boolean mechanism. So these four flows can be visually represented by the diagram on the bottom of this slide, from where you can find that there exists a path from Boolean to integer. So we have detected a potential bug. Okay. Those four formulas on the right of this slide are called type flows, which is a fundamental concept of our work. As demonstrated, type flows treat both ordinary value passing relations and typecasts in a uniform manner. So we can also alter the form of those value passing relations to mirror the form of typecasts. But they lack meaningful blame labels, so they are called dummy type flows. Hopefully, that awkward example has provided you with a glimpse of how static blame works. Now I'm going to provide an overview of static blame. So consider a gradually typed program and its dynamic semantics. Firstly, some runtime reinforcements will be applied to the source program. A typical example of runtime reinforcements is the typecast that we have already seen. Other kinds of reinforcements include type tags and coercions and so on. Then the program will run under certain blame semantics. So the essence of blame semantics is to defer static checks to runtime, and if an error happens, then the reported message should establish some sort of theoretical soundness of the type system of the language. So a well-known slogan is that well-typed components can't be blamed, right? Following this idea, those reported messages can be used to guide a debugging process. On the other hand, static blame begins with extractions of type flows. The extraction consists of a straightforward translation from ordinary value passing relations to dummy type flows and from typecast to type flows. Then static blame will perform the so-called type flow analysis. A crucial property about type flow analysis is there exists a strict correspondence between the result and the dynamic semantics of the program. Finally, static blame will tries to detect potential bugs based on the result. Among the process, I will focus on two key aspects: the correspondence and the methodology related to bug detection and reporting. So the correspondence relation is called dominance. It has two properties. The first property, which is called inclusion, states that all typecasts in the program should be contained in the analysis result if the analysis result dominates that program. It can also be succinctly stated by the diagram on the bottom left. The second property is that the inclusion relation should be preserved under reduction. So if the result dominates a program P1 and the P1 can be reduced to another program P2, then the result should also dominate P2, right? Formally, we proved those two properties in our paper. Roughly speaking, our algorithm proceeds by exploiting all possible typecasts or runtime reinforcements that may occur during the evaluation of the program. So this algorithm is therefore a standard over cross-mating analysis algorithm. The second aspect is bug detection and reporting policy. A potential bug is detected when we get an inconsistent type flow, because inconsistent type flows indicate inconsistent typecasts at runtime. For example, the standard blame semantics, as this slide shows, will abort with a blame message at runtime if an inconsistent typecast is performed. On the other hand, this inconsistent typecast should be obtained by the type flow analysis at a static time under the correspondence we have already seen. The bug reporting is another problem. So how do we locate the bug in the source code once we have detected a potential bug, an inconsistent type flow? In this work, we adopt a policy that strictly follows the blame semantics and identifies potential bugs with associated blame labels. So the position of a potential bug is the position indicated by the associated blame label. In other words, we assume that a blame typecast is likely to be contained in a buggy component. So in the previous example, the application itself can be considered to be a buggy component. So B1 is blamed, so we have successfully detected the buggy component, right? Of course, in the debugging process, the effectiveness of this policy depends on the blame semantics and the nature of bugs in practical scenarios. So in order to evaluate the effectiveness of the policy and the entire framework, we have implemented a bug detector based on selective blame on the language Grift, which is an academic language and can be considered to be a small subset of type-directed. So the evaluation is performed on the official benchmark of Grift, where bugs are injected by the means of mutation analysis. In particular, a bug report is considered to be a true positive if the reported location is contained in the actually injected bug. So the results of the effectiveness experiment are presented in the following table. Each row represents a different kind of potential bugs. The detailed definition is provided in the paper, but here the relevant fact is that lower rows are more rigorous in their criteria. So among those metrics, we focus on two columns, the precision and e-recall or estimated recall. The precision is defined as true positives among, the ratio of true positives among all bug reports. And the recall is defined as the bugs that can be detected by static blame. So the ratio of bugs that can be detected by static blame among all injected bugs. So as you can see, as the criteria becomes more rigorous, the precision rises while the recall declines as anticipated. So our experimental finding indicated that static blame is capable of finding bugs in practical scenarios, at least under our experimental finding. The main theoretical validity is that the representation of the benchmark is limited because the benchmark is generated by means of mutation analysis. So we have also discussed other kinds of theoretical validity in the paper. So finally, I'll summarize this talk. So the basic idea is to use flow analysis to detect bugs and to use blame semantics to report them. And more details are included in the paper. So thank you.
All right, any questions?
Thank you for the talk. So since you mentioned precision and recall, I infer that you can have false positives in your, this analysis can sometimes identify a problem if it doesn't actually exist. So like if that's the case, then like what are such examples?
Sorry, can you rephrase the problem?
I mean, maybe I'm misunderstanding, but like you use these measures when, for instance, false positives can occur, right? So that means that you
mean the cause of false positives or false negatives?
Sorry?
Do you mean the causes of false positives?
So what I mean is that does this analysis sometimes say that there exists a type mismatch where actually a problem would not occur at runtime? And if yes, then in what cases?
Yeah. So it's. I think you mean false positive. So the main cause of false positive is a subtle problem by the difference between the oblique message and an actual bug that we may intuitively define in our mind. So an example is that if, like this example, for example, assume that there is a value of type Boolean, but it is used as an integer as a program. So so if the type flow analysis reports a bug, but there is actually not, then it may be because that the value is not used. And so this is the first cause. And secondly, there may be containers in the program. So in the case of containers, we use the smash abstraction that we treat all elements like there is one element. So if the first element is wrong, but you actually use the other elements, then there will be a false positive. So we actually have discussed in detail the causes of false positive and false negatives in the paper.
Okay, right. Great. Thank you.
All right, I think we have a break now. So if there's more questions, you can ask the speaker, but I think we have a break for a half an hour.